Welcome to This Explainer. Today, we're diving straight into the tangible engineering of the global submarine fiber optic network. We tend to think of the internet as this invisible, wireless cloud just floating around us, right? But the reality? It's incredibly physical, surprisingly vast, and literally anchored to the bottom of the ocean.
Let's put this into perspective. A staggering 95% of all international data and telecom traffic doesn't go through space via satellites. No, it travels through a massive underwater web. We're talking about 600 active submarine cable systems stretching roughly 1.5 million kilometers across the seafloor. That's enough cable to wrap around the Earth's equator more than 32 times. Every global video call, every high-frequency financial trade, every international email, it's all literally speeding along the dark bottom of the sea. So here's our roadmap for today. First up, the ocean's invisible backbone. Second, trapping light in glass. Third, powering the deep sea. Fourth, laying the global network. And finally, fixing a broken internet.
All right, Section 1, the ocean's invisible backbone. Let's start by looking at the physical reality of the internet and just how cost-effective it actually is to wire our continents together.
What's honestly kind of mind-blowing here is the sheer economic feasibility of manufacturing these data cables, especially when you compare them to heavy power cables. To give you an idea, a heavy submarine power cable can run up to 2 million euros per kilometer. But subsea telecom cables, they cost roughly 25 to 45,000 euros a kilometer. It's this massive economic advantage, combined with practically limitless bandwidth, that absolutely cemented fiber optics as the undisputed champion of global communication, leaving heavy copper and satellite systems completely in the dust.
Now you might be wondering, how on earth do they survive down there? Well, to beat the crushing hydrostatic pressure and saltwater corrosion, these cables use 9 rigorous layers of protection. Right in the center is the active core, pure silica glass carrying the light pulses. Wrapping around that, we've got waterproofing gels, metal tubes for power, polycarbonate pressure layers, steel armoring, and chemical shields. But here's the crazy part. Despite all that armor, the deep sea variants, the ones way out where there's no human activity, are remarkably thin. They're only 25 millimeters thick. That's about the width of a garden hose, weighing just 1.4 tons per kilometer. Up in the shallow coastal waters, though, where you've got fishing boats and anchors dropping, that's a different story. Those require immense extra steel armoring to survive.
Moving on to Section 2, trapping light in glass. Let's zoom way in on that silica glass core, which, by the way, is roughly the size of a single human hair, and check out the physics that makes this transoceanic data transmission near instantaneous.
The whole system hinges on a physical principle called total internal reflection, combined with Snell's law. Basically, the glass core is engineered with a slightly higher refractive index than its outer cladding. When high-speed lasers fire a light pulse in at a very specific angle, the critical angle, the light reflects entirely inward. It doesn't leak out, it's essentially trapped, endlessly ricocheting down a microscopic glass hallway across the entire Atlantic or Pacific Ocean, carrying your data at literal light speed.
But wait, how do we push so much data through a single hair-sized strand of glass? Instead of laying thousands of individual fibers, coastal landing stations use wavelength division multiplexing, or WDM. This is a real game changer. Instead of just firing one beam of light, they transmit multiple independent data streams simultaneously by modulating them on completely different colors or wavelengths of light down that exact same fiber. Think of it like stacking multiple lanes of highway traffic perfectly on top of each other. Once the light reaches the other side of the ocean, ultra-sensitive photodetectors catch it, separate out the colors, and decode your data.
On to Section 3, powering the deep sea. Let's see how all this builds into an active, electrified grid that keeps our data from just fading into nothingness over thousands of kilometers.
So light is amazing, for sure, but it isn't perfect. As it travels, it actually weakens from scattering and absorption. To stop the signal from dying out, engineers splice in amplifiers called EDFAs every 50 to 100 kilometers. These basically run a massive relay race. They use redundant pump lasers to excite erbium ions inside a special section of the glass. When the weak, tired data signal hits those excited ions, it triggers stimulated emission, which is a fancy way of saying it perfectly clones the data photons, and the brilliant part? This happens purely in the optical domain. Older tech had to catch the light, convert it into slow electrical signals, boost them, and convert them back. But EDFAs? They just instantly boost the light itself, keeping things moving seamlessly and blindingly fast.
Of course, those amplifiers don't run on magic. They need electricity. The whole amplification system is powered by high-voltage direct current flowing right through that inner copper or aluminum tube we saw earlier. And get this, it actually uses the highly conductive ocean itself as a massive earth return, a giant grounding wire, to complete the circuit. Plus, smart hubs known as branching units are down there actively managing the routing. If a main trunk line snaps, these units automatically toggle between 4 different connection states to instantly isolate the electrical fault, ensuring the rest of the global network doesn't completely collapse.
Section 4. Laying the global network. Now that we've mapped out the internal tech and the power grid, let's zoom out. We need to look at the massive maritime effort it takes to actually put these cables at the bottom of the ocean.
There's a huge contrast in how this is done based on depth. In shallow coastal waters, anything under 200 meters, installation ships deploy heavy sea plows or these awesome remotely operated vehicles, ROVs, equipped with high-pressure water jets. They literally carve deep trenches into the sediment, safely burying the heavily armored cable up to 3 meters down to keep it safe from human activity. But out in the deep waters, plunging past 2,000 meters, there are no anchors or fishing nets down there, so they take the lightweight, unarmored cable and just meticulously, beautifully drape it directly over the untouched contours of the seabed.
Now, before a ship even leaves port, with the cable carefully hand-coiled into massive temperature-controlled tanks to avoid tangles, the prep work is just staggering. Operators have to secure incredibly strict international permits, they run advanced sonar and bathymetric surveys to plot a safe course around underwater fault zones, seamounts, and coral reefs, they need Marine Mammal Protection Act clearances so whales aren't harmed, biological opinions for endangered habitats, and amazingly cultural preservation reviews to make sure they aren't dragging a cable across a historical shipwreck. Building our digital future actually requires a massive effort to protect our marine and historical past.
Which brings us to Section 5, Fixing a Broken Internet. Because despite all that heavy armoring and obsessive route planning, the global internet still physically breaks roughly 150 times a year. Welcome to the high-stakes world of deep-sea repairs.
If we look at the fault data, natural disasters are actually not the big bad wolf here. It's us. Human activity, specifically ship anchors and commercial trawling nets in shallow waters, accounts for a massive 70% of all faults. That completely dwarfs deep-sea earthquakes, underwater landslides, or deliberate geopolitical sabotage. When a massive ship drags its anchor where it shouldn't, it can easily snag, stretch, or completely sever the digital lifeline of an entire nation.
So what exactly happens when your screen goes dark? Well, the split second a break occurs, network systems detect the drop, and landing station engineers immediately run an OTDR test. They fire a brilliant pulse of light straight down the damaged fiber and measure the exact time it takes for the backscattered light to reflect off the break and return. Because the speed of light in glass is a known constant, they can calculate the precise geographic distance to the fault. We're talking pinpointing a break out in the middle of the ocean down to mere centimeters. It is unbelievable.
Once they have those coordinates, a specialized repair ship races out there. Guided by strict international standards, fixing the cable usually takes 10 to 20 days and follows a critical 5-step protocol. First, retrieval, dragging a grapnel hook to snag and cut the broken line. Second, hauling both severed ends up to the surface, testing them and attaching buoys. Third, they bring it inside the ship's clean room, which is rocking on the waves, mind you, where technicians use microscopic precision to perform electric arc fusion splicing, seamlessly melting the new glass together. Fourth is executing the final splice, which creates an extra loop of cable. And fifth, relaying. Because of that extra slack, they can't just pull it tight. They use an ROV to water jet this massive, U-shaped final splice bite safely back into the seafloor sediment. As global networks lean heavily on geographic redundancy and live ship tracking to avoid those devastating anchor drops, the tech inside the cables is just rocketing forward. Researchers are already testing air-filled hollow core fibers. Instead of moving through solid silica glass, the light travels through microchannels of air at near vacuum speed. That's about 30% faster than solid glass. Seeing how far we've come, from thick, heavy copper wires to microscopically trapping light on the ocean floor, it really leaves you wondering just how much faster can the physical infrastructure of the internet truly get.